quite last maybe 10 years.
Yeah, at least.
Yeah. Stephan is currently a senior scientist at Atominstitut, Vienna, and he did his PhD from the same institute. You did his PhD with UG, right?
Yes, exactly. It was one of his first PhD theses. Actually, it was the second.
Yeah. He did his PhD in 2011, and Stephan is primarily an experimentalist, but have a very good understanding and good interest in the theory as well. And he is an expert of the Newton optics experiment and many important aspects of quantum foundations and quantum information theory. As mentioned, his primary research topics in Newton optical experiment, experimental realizations of many foundational issues such as quantum contextuality, error disturbance trade-off relations, that the one the Professor Ozawa has talked about, and the weak value and quantum Chasier cut and pigeonhole effects, and many more. And he has published around 50 research articles, and quite a number of them are in high impact factor journals like Nature Physics, Nature Communication, and NPJ Quantum Nature Groups, the Quantum Information Journal, and many PRLs and Physical Review Research, New Journal of Physics, and many more. I am particularly happy to let you know that we have recently had the collaborations and for an interesting experimental test of quantum computation relations using weak measurement. So today we got an opportunity to listen to him, and Stephan will be talking about the various aspects of quantum measurements and the theory and their experimental realizations. And with these words, I again welcome Stephan once again and invite him to deliver his lecture.
Okay. Alok, thank you very much for this very kind introduction. And again, I would like to thank the organizers for giving me the opportunity to present our experimental work at this wonderful summer school. So I try to share my screen. I hope this works. Yes. Okay, so 1 second. So you should see now the...
Yes, I can see.
Yes, okay, and I just need a spotlight, and then I can start immediately. So as you see, the title of my talk is Quantum Measurements. Sorry, it's quantum measurements, theory and experiments. As Alok already mentioned, I'm an experimentalist. Nevertheless, I would like to somehow focus on theoretical aspects and give the motivation why we do these investigations on quantum measurements and foundation of quantum mechanics, and not go too much into the details of our neutron optical experiments. So what you see here is our institute. It is located in Austria at the very center of Europe. It is close to the inner city. And here you see our building. And inside this building, we have a reactor hall. As you can see here, we have a 250 kilowatt trigger reactor. It's a research reactor. And this reactor is our neutron source. And as you see here, we have 3 dedicated beam ports where we do our neutron optical experiments. So we have a beam port for neutron interferometry. So neutron interferometry is single particle interference of massive particles. And as you see in this drawing, you see a neutron interferometer. It's cut out of a single ignot of silicon. It's a perfect crystal interferometer. And you really have a macroscopic beam separation. So the beams are separated, as you see here, indicated by this ruler, by several centimeters. This gives us the opportunity to manipulate coherently the individual parts of the interferometer. And with this setup, we did a lot of experiments regarding weak measurements or weak interactions, or the quantum Cheshire cat. And also, as Alok mentioned, introducing in our latest collaborations, we did a test of the canonical commutator relation. These are experiments we do with the neutron interferometer. And we also have another setup here. It's called a Ramsey or a polarimeter setup, where there's no spatial degree of freedom. It is only the spin degree. So the spin of the neutron is a pure quantum system, and it's the simplest quantum system you can think of. It's a 2-level system, spin up and spin down, but it offers a variety of opportunities to do experiments in fundamental physics. And then we also have a spin echo setup. Well, this is somehow a combination. You do have a beam separation, but this beam separation is small compared to the divergence of the beam. So we will focus today on experiments with the neutron polarimeter, or as we call it, the Ramsey setup. So here's a picture of our group. You see the head of our group, Professor Hasegawa, and some of our PhD and master students. Okay, so in 1927, Heisenberg proposed his seminal paper where he proposed a reciprocal relation between the measurement error and this disturbance of a quantum measurement process. And this is beautifully illustrated in the so-called gamma ray sort experiment, which is only based on the Compton effect, which is illustrated here. So the moment the position of the electron is detected, that is when the photon is scattered from the electron, its momentum undergoes a so-called discontinuous change. And this discontinuous change is the larger, the smaller the wavelength of the photon is, meaning higher accuracy in the position detection, small error, but large disturbance of a subsequent momentum measurement. And in the very same year, this famous relation was reformulated by Conrad, but now you see the measures are completely different. Now you have standard deviations, and these are statistical distributions, not of the composite system with successive measurements, but these are results, spreads of single measurements. So if you think of some n particles, then you take n half particles and measure the width of the position distribution, and with the other half, you measure the spread of the momentum distribution as it's illustrated here. So this is a kind of an intrinsic uncertainty every quantum system must possess. It has nothing to do with the actual measurement process, but this was the basic idea of the Heisenberg gamma ray microscope. So the unavoidable recall of any measurement device is ignored. This is the reason why we call this type of uncertainty relations preparation uncertainty relations, because this relation sets limits on how we can prepare our quantum state. So it is not possible to prepare a quantum state which is sharp in momentum and position, but it gives you no information of the underlying measurement process. And this is why we try to somehow schematically distinguish these two important types of uncertainty relations, which somehow there has been some confusion in the early times of quantum mechanics, but now we can clearly distinguish, and I would try to show it schematically here. So here on the right side, we have this so-called preparation uncertainty relations, where I prepare my particle, half of the particle are measured in position, half in momentum. We get the statistics, the width of the distributions, and get our uncertainty relations. And here we have it from position and momentum. And in 1929, 2 years later, Robertson generalized this uncertainty relation for arbitrary non-commuting observables A and B. And on the other hand, we have our measurement uncertainty relations. So here, regarding preparation uncertainty relations, the measurements are done on the single particle, different measurements. And here we have a joint measurement, which is done on the same particle, in theory. In practice, when we do experiments, we do it on the same ensemble. And if you take a look at the measurement uncertainty relations, there you have two subdivisions. We have the so-called sequential or successive measurements, where we have an error disturbance regime, exactly as it was in the sort experiment of Heisenberg. And this is in general not the same like a simultaneous measurement, where you have a so-called error-error trade-offs. And now the question is, what is the corresponding uncertainty relation to the Robertson preparation uncertainty in terms of measurement uncertainty? Is it simply that we replace the standard deviations of A and B by the error and the disturbance of measurement A and B? And the simple answer is no, it is not correct. It's not that easy. You cannot one-to-one correspond this to each other. You have to find new concepts. And this was done first by Professor Osawa, who also gave a talk, and I think it was in the first week of the summer school. And in 2003, he introduced this so-called universally valid uncertainty relations, where you not only have the two terms of error and disturbance, but you also have the standard deviations of the observers A and B. So you have three terms. The first term, the usual error disturbance trade-off, and second and third term somehow reflect the crosstalk between the spreads of the wave and the error disturbance. So we go now back to our schematic with a little bit more detail. So on the side of the preparation uncertainties, we have these typical measures like standard deviations as for Kennard or Robertson, or later Schrödinger. Also entropic relations, maybe we come to this later. So, and now here, for our measurement uncertainty relation, we need new measures. We need to define measures for error and disturbance. And there are at least three schemes I would like to propose and present today. So there's the so-called operator-based root mean square error proposed by Osawa. There's the difference between output probability distributions proposed by Paul Bush. We will focus mainly on Osawa's operator-based root mean square error, because in recent times there has been a lot of activities both on theoretical and on experimental side. But there is also the difference between output distributions, and the latest version covers so-called entropic uncertainty relations, where Buscemi and colleagues proposed in 2014 a nice procedure. Okay, so now we need to understand what happens in a quantum measurement process. And the most general system is a so-called quantum instrument. So we have our quantum system, which we call the object system with its Hilbert space. On the object system, we have, for example, our observable A, which is our target observable. So it is the observable that we want to measure. We have some state of the system, but we also have a second quantum system. It's the probe or measurement system, which has also an initial state, has a so-called meter observables. And at the very heart of our quantum instrument, there's a unitary evolution which acts on the composite Hilbert space of both object system and probe system, and introduces a coupling. And the idea is to transfer the value of our observable A to the meter observable of the probe system. And then we do a precise measurement of our meter observable. And the moment you do a so-called precise measurement with detection, there is no more quantum system. You have the collapse of the wave function, and all quantum information is gone. As you see indicated here, we have quantum channels in SIG. And after this precise measurement on the meter observable, we only have classical information, which is the classical output or the pointer. But on the other hand, here on our object system, we have a quantum output. And with this quantum output, we can do, for instance, a second measurement. Now again, we do a precise measurement. So the particle or the wave function collapses, the particle is gone, and we only have classical information. And with these two outputs, we can learn about successive measurements. So as we see here, we have a successive measurement of A and B, while the first measurement of A, you could call it's an approximate measurement because the information is gained through the coupling, whereas the second measurement is a precise measurement. And what we can study now, we can study the disturbance the first measurement causes on the second measurement. So, and this is described by a so-called POVM in general. So what we do a local measurement on our meter observable. It is local, as you see here, as it's indicated. So it's only a projective measurement on our meter observable. And with this, we have this expression for the measurement defining our so-called effects. I will explain it later in a little bit more detail, but these EM are the so-called effects of our measurement device of the quantum instrument. And it is important what we do here. We do a projective measurement on our meter observable. So projective measurements are a really important class of measurements in quantum mechanics because they have typical properties, which I will shortly summarize. So every measurement that can be decomposed into projectors times eigenvalues onto the orthogonal eigenstates of an observable are called projective measurements. Here you see the projector, and the projector has typical properties. So it's idempotent. So it is, if you multiply it with itself, you get the projector, and it's also an Hermitian operator, which is indicated here. And if you sum up all the projectors, they are complete. So you end up with identity. So for projectors, the expectation value equals the probability. You always get results that are bounded between 0 and 1 for the individual projector. And what is also very important is the so-called post-measurement state. This is well defined for projective measurements. This is not the case for all type of quantum measurements. As we will later see, for general measurements, the post-measurement state is not defined by the operator itself. But in the case of projective measurements, the moment you project your system onto the projector divided by the probability, and this gives you the post-measurement state. And as you see from this definition, which is also very important, if you repeat the one and the same projective measurement, the result stays the same. After the first projective measurement, the system is in the eigenstate of the projector. And if you repeat the measurement, as you see indicated here, nothing changes. So, okay, now we go back to our quantum instrument. So we do a projective measurement on our meter observable. And what happens is that the effect that results here itself is not necessarily a projective measurement. This depends on the unitary evolution here. So this unitary evolution describes the measuring process acting on the composite quantum system consisting of measurement of probe system and object system. And the effects themselves do not need to be projectors. In general, they are so-called POVMs, positive operator value measurements. And this is the most general form of a quantum measurement, which results from this procedure, meaning from the partial trace of the measurement system. Of course, projective measurements are a special case of the POVMs. So what are the other properties of these POVMs? As we see, a POVM determines only the probability of a certain output. So you have these so-called effects, EMs, and for every EM, there's a certain probability, which you can calculate either here for pure states or for mixed states. And again, they also add up to identity. So it's a complete system, and you get these probabilities as described. And also, of course, the effects themselves add up to identity, and the probabilities add up to 1. So, and now the question arises, well, what happens to our quantum system? What is the state after the measurement? And unlike for the projective measurement, the POVM itself does not contain enough information to tell you what the post-measurement state is, because therefore you need to decompose the POVM into its Krauss operators, as you can see here. And it's the Krauss operator that defines the post-measurement state. And if you compare it to a projective measurement, well, as we know, if our effect is a projector, then of course we know it's Hermitian and it's idempotent. So in the case of a projective measurement, the Krauss operator and the POVM is the same, and then it is possible to calculate the post-measurement state. But in the case of a non-projective POVM, you need to know how the Krauss operators look like, and this is not, and in general, there's an infinite number of decompositions. So that's why you can simply say the POVM only gives you the probability of a certain measurement outcome, but gives you no information about the post-measurement state, or it's ignoring it. So maybe we take a short look at a very simple example. So we have a measurement device that measures the state, the ground state and the excited state, but somehow maybe to get a realistic picture of a measurement device, with some probability P, it's not working at all. So these are our three effects. Of course, if in case 3 where it's not working, you don't get any information. And already this very simple procedure cannot be explained in the framework of projective measurements. So already for this simple example, you need a POVM. Or we can take a look at another more elaborated example. So we have 3 effects here, E1, E2, E3. They look like this. And you might wonder, well, what can be the use of these 3 effects? Well, you see, they add up to identity. It's a valid POVM. These effects are able to distinguish between non-orthogonal states, for instance, between the ground state and the superposition state in X. This is not possible by any projective measurement, because you see here, if you calculate the probabilities for the individual effects, dependent whether you have to measure state 1 or 2, you see here, if you get output 2, then you can be sure that it was not state 1, because you have, in this case, 0 probability for that. Or if you get effect 1, you know that it's not state 2, because for state 2 you have 0 probability. But of course, there's a price to pay for this information. Namely, as you see, E3 is more than 1/2. So in more than half of the cases, you get no information at all. So there's no way around, but it's a really interesting example. Okay, and now we come back to Osawa's universally uncertainty relation. And now we have to understand how error and disturbance are defined using the concepts that we have introduced in the slides before. So again, we take a look at our indirect measurement model, our quantum instrument, and somehow, of course, the classical output of our observable E must somehow be related to the error, whereas the result of our B measurement must be connected to the disturbance. And this is expressed in a very elegant way using the so-called noise operator. So here you see the noise operator, and its expectation value is the noise. So this should not be somehow confused with some measurement error. So what this operator does, it tells us how accurately the value of an observable E of our object system is transferred to the meter observable of our probe or measurement system during the unitary evolution of the composite quantum system. And in the very same manner, we have a definition for the disturbance. It's simply the value before the measurement minus after the measurement. Okay, and then I will not go too much into detail, but if you now calculate exactly error and disturbance here, you find again, it's the same procedure as before. You get a POVM, and it is now this object, which is acting now only on the object space, because here you have the initial state of the probe system, so it's a partial trace. And in the case of our thing, if these measurement operators are orthogonal projection operators, then we can exchange summation and norm. And in this case, we find a very compact expression for the operator-based root mean square error, which is simply the difference between the so-called approximator, which is called OA, which you can see here. It's the decomposition of our measurement operators minus our observable E. And with this, we have a valid definition of the error of a quantum measurement expressed in terms of operators. And that's why this is called the operator-based root mean square error, as you see here. And you can do exactly the same calculations also for the disturbance, where you get this formula. It's a little bit more complex because you have the commutation relation here, but in principle, you have for projective measurements a very simple expression. So, and now we come back to our question, well, how does the measurement uncertainty relation that correspond to our Robertson preparation uncertainty look like? We already know that it's not this. And now we can really see why this is the reason for it. Because if we go now back to projective measurements, for instance, a simple spin measurement, and if we plug in our definition of the error, we immediately see that in case that A equals OA, this will be 0. So in that case, we would have a so-called noiseless or accurate measurement. And for discrete systems, we immediately see that the disturbance is bounded, so it's less than infinity. So we see that projective measurements of A are able to satisfy that error times disturbance are 0. So this is a very simple example that shows us that the straightforward generalization of Robertson preparation uncertainty to a measurement uncertainty is not correct. And we now want to look at how to measure the individual results of Osawa's University valid uncertainty relation. Well, what is the problem? Why can this not be simply measured? If you look at the definition of the error of the quantum measurement, you get something like this. This is a joint expectation value of incompatible observers. So in general, this cannot be measured directly. As Alok knows, this can be measured using weak values, but this is not the scheme that has been chosen here. The solution to this is the so-called three-state method. So if you take again a look at this operator identity, you see that you can add identity as you always do, and then you get these three terms. And now if you plug this into the expectation value, you see that you get some kind of symmetrization. So instead of having a product of two non-commuting observers, you get expectation values not only of the initial state, as you have it here, but also of some auxiliary states. So the A here acts on the left side, changes the state psi to psi dash, and it also acts on the right side and changes psi to psi dash. So what you see, you get a number of expectation values of single observables which are measurable. And now we go one step further. Now we say our observers are not only projective measurements, they are a very strict type of them, namely the so-called Pauli spin matrix, because Pauli spin matrices have additional properties, namely that the square of a Pauli spin matrix gives identity. So if we take a look at our expectation values, you see that the two of them add up to 1, and we're only left with 3 expectation values in 3 different states. So the expectation value of OA in state psi, and OA in state psi dash, and psi double dash. So the interesting thing about this concept is that we want to measure the error of an observable A, but in no instance there's really a measurement of A itself. It's only that A enters into our auxiliary states, which are used for the measurement of the error. And we simply get exactly the same for the disturbance, where we also have different states that need to be measured to get a value of the disturbance. So, and we have now 2 operators which we already introduced. So when we want to measure the error, there's the so-called output operator, or it's the approximator of our measurement. And for the disturbance, we need the so-called modified output operator. As you see here, it somehow tells you how the observable B of the second measurement is modified by the measurement operators of our first measurement. And this is the source of the disturbance. And you see here, the error is given by expectation values of the output operator, of the approximator, while the disturbance the successive of second measurement is given by in terms of expectation values of the modified output operators in also 3 different states. And this is how the actual measurement would look like. So you have a preparation where you prepare your different states. You send them onto the successive measurements of A and B. So the first measurement is our approximate measurement, which is indicated as OE. There's 2 output ports. We have Pauli spin matrices. They have a plus and a minus output. And then you do a precise second measurement of an observable B, which has again 2 outputs. So in total, you get 4 outputs. And I don't want to go too much into details, but by cleverly arranging these 4 intensities, which can be straightforward calculated here, you get simple expressions for the expectation value for the output operator and for the modified output operator. And then you repeat this with your initial state and with the auxiliary states and sum them all up. So now we come to the actual example or the actual experiment where we now fix our observables. So we set our observable A to be sigma x, B sigma y, and our approximator shall be in the equatorial plane ranging between E and B, and our initial state is set to be plus Z. Then again, we have our quantities for error and disturbance. Now we plug in A and B. We see that the initial state changes sometimes from plus x to minus x or to plus minus y. So, and this is the actual neutron interferometric setup, as you have seen on the first slides, with a preparation stage where we prepare the initial state, but also the auxiliary states. We have the first measurement, the approximate measurement of A, and we have the second measurement, the precise measurement of B. So I will skip the slide. I just want to give you an idea what is the physical mechanism behind all these measurements. Well, it's a so-called Lama precision. So our observable is the spin of the neutron, and the spin precesses about the magnetic field. And this is done with a frequency, and this frequency is called Lama frequency. So the longer the polarization with vector, which is the expectation value of the Pauli spin matrix, is exposed to the magnetic field, the further it precesses. Or if you have neutrons that have all the same velocity as in our experiments, it only depends on the strength of the magnetic field, how far the rotation on this cone goes. And by this mechanism, you can both prepare states by rotating your initial polarization into another direction, or it's exactly the same for analyzing your spin simply by rotating it back. Okay, so I will just move on a little bit to the actual results. So this is it's a picture of our setup. So this is again our research reactor. There's a monochromator which selects only neutrons with a certain velocity. In our case, this is 2000 meters per second or 2 angstrom. This is chosen because it's the maximum of the intensity of the reactor. And here you see the various coils where the magnetic fields are produced that manipulate the neutron spin. Here you see them in more detail. Okay. These are some typical measurements. So what we do, we measure in these 3 auxiliary states. We have 4 output channels because we have a successive measurement of Pauli spin matrix, and we get 4 intensities. And when we arrange them accordingly, we get values for error and disturbance. And here you see the first results. And what do we get? Well, simply, if we set the approximator to A, so we have some detuning angle which we set to 0, then A and OA are the same. In that case, we have a precise measurement of A, so we have 0 error, but of course the price to pay, then we would disturb the subsequent B measurement maximally, so it would be random, so this is not what we want. So this is why we changed the tuning angle by rotating our approximator away from A towards the measurement direction of B, and you immediately see what happens. The error goes up while the disturbance on the subsequent B measurement goes down. And in the end, for a detuning angle of pi half, the situation is inverted. Then we have a precise measurement of B with 0 error, but with 0 disturbance, but a maximum value for the error. And what is also very important here, this error is state independent. So as you see here, for the theoretical predictions of error and disturbance, they only depend on the detuning angle. So this is, you would get exactly the same result if your initial state would not be set, but anything else. And of course, we've done a lot of measurements, and we also experimentally verified that in the case of Pauli observables, the operator-based root mean square error is state independent. And this brings us to a very important property, which is called soundness, as we will see later in the talk. This error is a sound definition, which simply means that the error vanishes for an accurate measurement. So when do we have the accurate measurement? Of course, if the approximator and A are the same. So for detuning angle 0, we have 0 error, and that makes our measurement accurate. So the operator-based root mean square error is a sound error measure. Okay, and we see here, if we now combine error and disturbance, we see that we also go to 0. So you could say it's a violation of Heisenberg's original error disturbance uncertainty relation, but as we've seen before, this is not valid. That's why we had the definition of Osawa's uncertainty relation, and this is always well above. So as I said before, we do not only need error and disturbance of the subsequent measurement, but also the standard deviations. So they are measured on the separate systems. And then if all this data is combined, you see here in orange, the left side of Osawa's uncertainty relation, and this is always above the limit, whereas the simple product of error times disturbance, which would be the naive extension of Robertson preparation uncertainty, is always below, whereas Osawa's universally valid uncertainty relation is always above this limit. Okay, now we come to the second topic that we want to cover, and this is called soundness and completeness of root mean square errors. As you see here, Professor Osawa already gave a talk, as I mentioned, but no, it's no problem if you missed it, because I will summarize all the results that have been presented in this talk, and we will see the results. So we already discussed the important property of soundness of an error definition, but what is completeness? Well, in a recent example, Bush, Heinrich, and Latti presented a so-called counter example. Namely, they presented a measuring process that is not accurately or not precisely, but it has 0 error. And this is the example that is presented here. So we have an observable A, which is simply identity plus sigma x. We have an observable M. This M is what I used to call in the slides before OM. So this M is the approximator. So it's the approximate measure of A, but I did not change it because I wanted to stick to the original notation of the papers. And you have an initial state, which is simply set. And as you see here, this measurement is somehow a little bit specific. Well, it is a projective measurement, but it is not a measurement of pure Pauli observables. And this makes this measurement a state-dependent measurement or a state-dependent error. And if you see here, if we plug in our definitions of the operator-based root mean square error, we get 0. And this somehow brings us into a problem because, as we see here, of course, M is not an accurate measure of A. Nevertheless, the quantum root mean square error gives 0. And this is what is called completeness, or in this case, it's the incompleteness of the quantum root mean square definition, because the completeness is the inversion of soundness. Soundness means if the measurement is accurate, the error is 0. And the inversion should be if the error is 0, this should mean in turn that the measurement is accurate. But as we see here, M does not accurately measure A. I will not go too much into details. So the simplest explanation is the eigenvalues of A are 2 and 0, whereas the eigenvalues of M are plus minus square root 2. So these two observers have disjoint spectra. And if you have disjoint spectra, then the projectors cannot be the same. So this is 0. So M, the projectors, the POVM of M cannot accurately measure A. It's not an accurate measurement. But the problem is that the error nevertheless is 0. And this, of course, calls for a reformulation of the error. So there must be something corrected in the root mean square error definition to make it complete again, meaning that for an inaccurate measurement, the error should not be 0. And this was done in a very recent paper published by Osawa in 2019, where he proposed, in addition to the noise operator root mean square error, a so-called error profile. And as you see here, the definition simply takes the definition of our operator-based error disturbance, and it is multiplied by a time evolution, and the state, the initial state, is multiplied by a phase factor, a time evolution that is dependent on the observable A, and then simply by taking the supremum, the largest value of this is then the so-called local uniform quantum root mean square error, and this is the valid definition of an error measure, which then again is sound and complete. And if we take a look at the example that we had before.
Stephan,
yes,
I have a question. I mean, I heard this talk also. I mean, that why this introduction? Because what does it mean? A pi e to the power I t a. Why this additional unitary evolution you are introducing? So then taking suprema over all t. What's the physical motivation behind this? I mean, can you please reflect? I mean, give it some.
Yeah, the physical motivation behind this is we still have a projective measurement, but unlike the case of Pauli observers, now this is a space-dependent error. And this somehow was overlooked in the initial definition. The definition suits well for Pauli observers because there the error definition is state independent. So you can plug in any state, you will always get the correct value for error and disturbance. But since this measurement process here, it is still projective, but it's not in type of Pauli observers. And that's why a state dependency enters. And it was somehow overlooked at the beginning. Of course, if you do general measurements like other POVM weak measurements, then it is obvious that these measurements are state dependent. But here you have the special case where you are still in the regime of projective measurement, but it's not a measurement of Pauli observers. And so from the back door, a state dependency enters into the error definition, and this has to be taken into account. And this is exactly what this definition does.
Then it becomes state independent.
Exactly, yeah.
Yeah. Okay. Please go ahead. Yeah.
And this is what you see here. Now, again, this local uniform error now is no longer state dependent. It only depends on t, a time parameter or some evolution parameters. And this, of course, is fixed when you look for the supremum. Of course, it does not tell you what will be the value of it, but this is what's in the experiment needs to be confined. So, and then we have a so-called sound error definition. So it vanishes for any accurate measurement, and it is complete, the invasion. Should be accurate if it vanishes. It has two other properties, the so-called dominating property. So it's always larger or equal compared to the old definition. And what is also very important, the so-called conservation property. So in case of Pauli observers, which as we discussed have this property, then everything remains the same. Then the new definition coincides with the old definition. That is also very important because that means that all our previously observed results, of course, remain correct, because in that case, we analyzed Pauli spin matrix. So, and now we need to go back to the experiment. We need to understand what this evolution means for our spin of the neutrons. Well, it's very simple. If you plug in this phase factor, you immediately see that this corresponds to a rotation about the x-axis. So our time-dependent initial state is now an angle dependent, which is our experimentally accessible parameter. So what we need to do, we simply need to rotate our initial state about the x-axis. It is the x-axis because this is because our observable A is given by identity plus sigma x. So identity in that case drops out, and sigma x induces a rotation about the x-axis. Now we do the projective measurement. So we need to decompose M into its projectors. As we have already seen, M has our eigenvalues plus minus square root of 2. So it's decomposed into square root 2 projector to plus minus projector to the eigenvalue minus 2, which have exactly this form. And then we have almost the same as we had before. But now the difference is, now we have two additional terms. Now, since we have no Pauli observables, these two terms are no longer one, so they have also to be measured. Again, this is our setup. It's a little bit simpler in this case because now we are only investigating the error. And yeah, I will not go too much into detail. And here, what we do, we measure all these terms. It's simply here we have to measure the projector onto plus x for all our initial states. Here we have to measure identity, and the other ones are the projective measurements of our observable M along these directions. And if we sum up all these terms, so just go to the end, then we get this. This is the so-called error profile. And now we immediately see, well, here we have a local maximum, and this local maximum is now our new valid definition for the error of this measurement. And as you see, the error depends on the choice of the POVM, and in our case, the POVM of the measurement process is a projector. So we have a maximum value here for this. Okay, but as I said before, it's also interesting to take a look of other experimental realizations of this measurement, namely in terms of POVMs. As I said before, we have basically two large classes of measurements. We have the sharp or projective measurements, and we have the unsharp or generalized measurements. And if you want to analyze the generalized measurements, you not only have to take into account this first term of the error definition, but you also need to take a look at the second term, which has not only the observable, the meter observable, but it also has its second moment. Why was this not necessary? As you see, you have here the definitions for the mean of the operator and the second moment. Why was this not necessary in the case before? Well, before we were dealing with a projective measurement, and in the case of projective measurement, the mean operator and the second moment operator are the same, and that's why this term vanishes in the case of projective measurement. But if you realize the M measurement in terms of a POVM, which is not projective, then you also have to consider the second moment operator. And this is what we see here. So now we do a different decomposition of M. It's in terms of POVM with eigenvalues plus minus 2. As you see here, it's simply identity plus minus 1/2 sigma x plus minus 1/2 sigma y. If you add this up, you also get M. But now this decomposition is in terms of POVM, because this object now is no longer a projector. You can write it in a simple way. You can say it is something like a combination of a projective measurement together with a no measurement, or it's you could call it a noisy measurement. And now if we want to analyze the error of this measurement, we do exactly the same as before. But the difference is now we also have to take into account this term where the second moment occurs. And you see here's some illustration on the Bloch sphere where the POVM elements are simply indicated by shorter arrows on the Bloch sphere. What you do in the actual measurement, so now you combine, as you can see here, the POVM is a combination of a projective measurement indicated in yellow, which we have here, and it's a no measurement of identity, which is simply in that case realized by measuring along the x-axis, and then by randomization you get the correct weights. And if you put the two results of the no measurement from the identity and the projective measurement together, you get a measurement of the POVM pi 2. And this is the interesting result. So what we see, the result of the M measurement is the same, both for the projective and the POVM measurement, because both are valid decomposition of one and the same operator. But as we will see on the next slide, the error will be different. So what is different is here are the individual measurements. Here we compare the experimental results of the projective measurement in red, and here the POVM measurement in green, and the same for minus the projective measurement for the eigenvalue square root 2 and the POVM for minus 2. And if we combine the two of them and add them up, as it's the definition of M, we get results for the M measurement. The results themselves look almost the same, but what is different, I will skip the individual results. Yeah, what is different is the error. So which tells us what happens with the system. So for the when you analyze successive measurements, you immediately would see that you get different results, and it's the same here. So again, the error for the POVM measurement is taken as the supremum, which is square root 6, and here for the projective measurement, the error is given by 2. It's the supremum of this curve. So what this tells us is the error of a measurement is not only defined by the observable itself, it is defined by the POVM, by the actual measurement operators, which is indicated here. So the error depends on the POVM. If you decompose the measurement into projectors, you have a projective measurement, a sharp measurement, which gives you a smaller error compared to a general measurement, namely a POVM measurement, which gives you a higher error. Okay, so with this, I would like to move on a little bit to the last chapter of my talk. Namely, now we take a look at a different error measure, namely an so-called entropic or information theoretic error measure, which was introduced by Buscemi in 2014. And the motivation again is the same. So if you take a look at our preparation uncertainty relations, we already have standard deviations, but we also have entropy. So in 1983, David Deutsch introduced a entropic version of an preparation uncertainty. And of course, as before, there should be also a corresponding measure for measurement uncertainty relation. So what was the reason to reformulate preparation uncertainties in terms of entropy? Well, the well-known Robertson relation has at least two flaws. First is it can become zero even for non-commuting observables. This is due to the state dependency of the right side of the preparation uncertainty relation, as we see also here. And the second problem is that standard deviations are not always the optical measure for certain states. I will not discuss this too much in details, but there are several counterexamples that show that the left side of this equation can go up to infinity. So what is the idea? We should look for an uncertainty that has this structure, namely the left side, some function of our observables A, B, and the initial state, but the right side, the limit, should not depend on the initial state. It should be a state dependent. So, and it should only be zero for commuting, so for compatible observables. And on the other hand, we want to have that the left side of our uncertain relation should always be less than infinity, and it should be zero only if psi is an eigenstate both of A and B. And according to Deutsch, this is exactly the case when the measurement of single observer is defined by Shannon entropy. So maybe we can take a short look at what is meant with the information theoretical concept of entropy. So what we need is a so-called sample space. So for example, it could be coins, or could be cards, or could be dice. And then you want to calculate probabilities. You have a probability function, which simply tells you what is the probability for a certain coin, card, or dice. And as we know, all these probabilities have to add up to 1. And now we want to find a definition for information, because entropy is related to information. So what should be the connect between information and entropy and probabilities? Well, information should be non-negative. It should approach zero for events that are certain. And then information should go to zero, and it should increase when the probability goes up. Well, so we simply can introduce something that is called the self-information or the surprisal, which is simply the logarithm of the probability. So if the probability is very high, the information, the self-information or the information gain goes to zero. If something is very likely to happen, then you don't gain very much information. And the less probability it becomes, the larger the information becomes. And with this with this information, with this concept, we can define the so-called Shannon entropy. The Shannon entropy is the weighted average of the self-information. So the self-information is given by the logarithm of the probability, and then it is multiplied by the probability and summarized over all regions. And this is the entropy, which has some different properties now. So now it looks like this. So the entropy on the right side for high probabilities goes to zero, exactly as the self-information. But due to the weighting with the probability, the entropy also goes down for very unlikely events. And as you see here, the maximum of the entropy is given when the probability is 1/2. So this is the largest information gain. We can take a look at this, for example, if we do a coin toss, where we have 1/2 for heads and 1/2 for tails. Here, the entropy is 1. So the maximum information gain of 1 bit is when the probabilities are equally distributed. So it's So the entropy has the same properties like a random variable. This is a very important property of the entropy. And using this definition, we can move on to a quantum version of it. Well, what is the probability? Well, it is simply the product of an eigenstate times our initial state. You get a probability of measuring A. You have the logarithm of it, is the self-information. And if you sum up over the eigenstates of the observable A, then this property gives us the entropy or the information theoretic uncertainty in terms of a preparation uncertainty, which was defined like this. But again, now we are still on the side of the preparation uncertainty relations, but we want to translate this into measurement uncertainty relations, meaning that we have to analyze subsequent measurements. And this is the reason why we need to have a look at multiple events of two subspaces A and B. And here the appropriate measure is the so-called conditional entropy or the conditional probability, which is simply expressed here. There's a very short, simple example of it. So what this means in daily life, if you smoke, you are likely to get cancer. But simply state that smoking causes cancer is too easy. So in that case, you only need to find one person that smokes and does not have cancer. So then this statement would be wrong. But what is correct is that the probability to get cancer is higher if you smoke. And this is expressed by the conditional probability, which is given here and tells you what is the probability of a joint event given that one event is certain, or you can see it here on the event space. It's just a very simple example, which we will skip now. It's just tells you the same with numbers. So, and now we come to our information theoretic concept for entropic noise and disturbance definitions. So the idea that was presented by Buscemi in his paper is the following. You have a system with eigenstates and they are randomly chosen. And then they are sent onto an apparatus that is carrying out a measurement. It might be a projective measurement or it might be a generalized POVM measurement. And then you have a classical output. And the question is, how well can I infer from the output statistic which eigenstate was sent onto my apparatus? If I can guess this with certainty, then the noise is zero. Of course, this would be only possible if the measurement apparatus measures along the eigenstates of my observable A. In all other cases, the noise, which is the corresponding property to the error before, will be non-zero. And this you can simply express as the condition probability of observing output M, given that the state A was sent onto the measurement apparatus. And exactly the same can be done for the disturbance. Here the disturbance quantifies the loss of correlations between this eigenstates of observable B that are sent on the apparatus and on the result of the second measurement. As before, the second measurement is a precise measurement of B. And then you have the output statistics. And again, the question is, how well can I guess from this output which of the initial states was sent? And of course, there is a loss of correlation unless this measurement is also the same like the B measurement. But in general, the first measurement will be different, and this causes a loss in correlation. A part of this loss can be corrected when applying an error correction, but there's always a part that can not be gained. And so there's always a loss of correlation, which defines the disturbance, which we also express here with the conditioned probability B and B dash. B are the states that are sent on the apparatus, and B dash is the statistics after the second measurement. In our case, again, we are working with neutrons, the spin of neutrons at two-level system. So the same applies, of course, also if you only have two states. And then we can take a look at our state-independent noise disturbance trade-off relation, which is of this form. The measurement setup is not very different from before. We have a preparation scheme where we prepare eigenstates of A, namely plus Z and minus Z, and B plus minus Y, send them onto the apparatus. The first one does an approximate measurement of A, whereas the second one does a precise measurement of B. And in between, there's also a correction operation to minimize the disturbance on the B measurement. Here we have our outputs. I will skip this a little bit and come to the results. And what you see, it's a very similar result compared to the error disturbance in root mean square definition. So the noise is 0 for 0 detuning, and the disturbance is maximum. And then when I move away with the approximator, the noise is going up, whereas the disturbance is going down. Here we have two different values for disturbance. So one is the disturbance without the correction operation, where all correlation loss can be seen, whereas the optimal correction, where you change the state between the two measurements depending on the result of the first measurement, this shows you that some of the loss correlation can be gained back, and we get, for the same amount of noise, get less disturbance. And you see here, you can plot the noise against the disturbance, where you also see that the uncorrected boundary is higher compared to the optimally corrected. And what is, I'm almost running out of time, but the last thing I want to show you before I quit is that it was pointed out in a recent paper by Bronsard and Abbott that projective measurements are not always optimal here in this noise disturbance region. So somehow this seems to be a slight contradiction to what I've shown you before, because in the measurement before, we learned that projective measurements have less error compared to general or POVM measurements. Well, that is correct for the error of a single of the first measurement. But what we study here is the trade-off of noise or error and disturbance of a successive measurement. And here it was really found out that a certain general measurement, namely a 3 outcome POVM, is able to outperform projective measurements. This was what we see here. So in red, we see the result of the projective measurement as we had before. And then it was proposed that a 3 output POVM might perform better. And this is what we see in the experiment. So the proposed 3 output POVM can be illustrated like this. So it has somehow a measurement direction, and it has a weighting. So it's, again, it's somehow a decomposition of a projector together with a weighting function. And I can show you a simple movie of it. So you see the 3 arrows represent the 3 POVM elements. And you see for 0 and pi half, you get a projective measurement in X and in C direction. So again, here I plotted this for 3 distinctive values of the parameter. As you see, for pi half, the POVM is simply a projective measurement along the C axis, whereas here for 0, it is a projective measurement along the X axis. Because it is complete, because these two here coincide. So if you have the information about the first measurement, you can calculate the rest. Okay, and this is the result. Again, the setup is not very different. And this is what we get for the noise. So again, we compare now our 3-output POVM to the projective measurement. Well, as before, the noise, which is the information theoretic corresponds to the error, is larger in the case of POVM compared to projective measurements. But if you combine this with the disturbance, you may already get an idea. So even though the error of the POVM measurement is larger, but the disturbance is even stronger reduced. And this is the final result. So here you have the noise disturbance plot for the projective measurement that we had before. But the projective measurement, surprisingly, is outperformed by this particular 3-output POVM measurement over the entire race. And here are the 2 points where this 3-output POVM and the projective measurement coincide. But in all other regions, this 3-output POVM gives a better noise disturbance trade-off compared to the projective measurement. And with this, I would like to quit and thank you very much for listening to me for a few minutes longer than expected. Thank you.
Yeah, thank you very much, Stephan, for this beautiful and really interesting and very good talk. The session is open for questions. So, is there any questions from the students?
So, as you already see from the last slide, I also planned to talk a little bit about the definition from Paul Bush regarding the differences in output probability distributions, but I ran out of time. I will do this the next time.
A lot of results. Many results are there.
Yeah. So that's why, but I decided to focus more on the more recent results from the Osawa experiments.
So I have a question. In fact, I have quite a few questions. So can you go back to the earlier slide, what you showed?
To which slide? To
earlier slide, just earlier slide.
Mm-hmm.
Yeah. So
this one.
So here you consider the 3 outcome POVMs, and that actually beating the projective measurements thing. The one, the Francesco, they have shown this in 2014, but in the work they showed that if you take the 3 outcome POVM, sometimes POVM performs better. I mean that means that optimal value may not be available always for the projective measurement. Sometimes POVMs gives a better results, like in this case.
Yeah, for successive measurements. Not for single, exactly, yeah.
Because now the thing is that the POVM are considering, these are actually the extremal POVMs, right?
Yeah.
And now why this is the 3 outcome, why not? Because there's a extremal POVM in the qubit system. There are 2 kind of extremal POVMs. One is the 3 outcome, the one, the time-spin axis you have considered. And another one is this SIG POVM. It's a symmetric informationally complete POVM. Yeah. Yeah, if you use that one, that may give something a different optimal. I mean, because this is symmetrical information complete, if you take the 4 outcome POVMs. So that may give, is there any idea that it can give better result than this 3 outcome POVM?
It's a really good question because this was discussed a lot. Because this discussion does not apply the experiment, but the theory, because this 3 output POVM, there's no general proof that it's optimal, but it performs better than the SIG POVM. It performs better than 4 output and other POVMs. But Cyril and his colleagues, they are still working on a rigorous proof to show that this 3 output POVM is optimal. It seems to be optimal just in that case that no better one was found. With various, there were computer simulations which were calculating tens of thousands of 3 output and 4 output POVMs, and none of these POVMs performed better than this particular. But the rigorous proof for the optimality of this 3 output POVM is still pending, but that's work in progress on the theoretical side.
Okay. So there's a possibility that maybe the SIG POVM can provide better results. Yeah.
Of course, you can find some trivial equivalent POVMs, but just some relabeling or swapping. But really, you have to find a really different POVM that performs better was not achieved until now. It's really interesting topic.
Yeah.
And interesting is,
yes.
yeah. And also the numbers of effects. So if all 4 output POVMs seem to perform worse than this 3 output POVM. And if in general, if the number of effects goes up, the trade-off becomes worse.
Okay. Well, there is one more question here from Sarang Bhosle that noise. Should I read it for you now?
Sorry, is it in the chat? I see it. So yeah.
Okay, I can read it for you. The noise has so far been always discussed in terms of something that destroys quantum correlations.
Okay,
but is it possible that sometimes noise actually enhances the correlation or help us in sharp measurement?
Yeah, okay, so this is somehow a confusion in the terminology. So the problem is what is called noise is error definition. It's not the noise that you usually have in a noisy measurement or in a quantum channel that destroys your coherence. This noise is a quantity that defines the error of a measurement. I actually personally say it's a bad choice to use the word noise. It's totally confusing because, like in this question, everybody thinks that noise is something bad that destroys your measurement. Here it is an information theoretical definition of the error of a quantum measurement. And for some reason, I don't know why it is called noise, but it should not be confused with a noisy channel in a quantum instrument. This is something different. So the noise here is simply the information theoretical or entropic definition of the error, and not noise as we usually will think of it. That's a very good question because that's somehow confusing. Yeah.
Alok, I have a question.
Yes, sure. Please go ahead.
Yeah, Professor Sponar, first of all, extremely nice talk. I really got educated about this thing, and we were lacking this type of talk. And
Thank you very much.
Informally, Professor Bush visited when he was with Alok's conference. He also came to ISO Kolkata, and we were all very emotionally attached to him.
Yeah, I also met him 3 years ago at the conference, and we could also talk about his contributions to the field. I'm sorry that I did not have the time to present his error measure, but I'm sure we can do this in another session, and maybe even.
My question is that where does weak measurement fit in here? In weak measurement?
Yeah. Well, if you would do a weak measurement instead of the POVM or it would be somewhere here in this region. So the weak measurement performs much worse because it depends somehow on the parameters, but the typical property on the weak measure, if you have the broad distribution of the pointer state, is that in general, the error of the weak measurement is very high. So if you apply these error measures, also Osawa's error measure to weak measurements, also a type of a generous measurement, this gives in general much higher errors compared to this POVM or compared to the projective measurement. So as you see here, for example, when we only compare the noise or the information theoretical error, here we have the projective measurement, here we have this 3 output POVM. All weak measurements would be in a regime very close to 1. Dependent on the width of the point. Of course, if at some instance the weak measurement can converge to a projective measurement in that case, but in general, the noise or information theoretical error of weak measurements is very high. That's the.
Makes sense. Yeah. Thanks, Alok. Yeah.
Okay. So if there's no more question, I can want to ask one more.
Of course.
Yeah. So in the one that when you showed that how Ojawa, Professor Ojawa has modified this his noise error expression to the state dependent to state independent. That to go back to this slide, I just want to see that what you are exactly measuring in it.
Yeah. So I go back to the definition. 1 second. Oh, it's here.
Yeah, go down.
Yeah. So
yeah, I understood. I mean, that what you are measuring, that how the state independence is coming back. Yeah, here. And how you can show this state independence is here. How it is.
Yeah. Okay. Because we can see that I will.
Yeah, this is the definition.
Yeah. So we plug in the definition here.
Yeah.
And we see that so this phase depends on the observable A.
Yeah.
And this tells you how your initial state is modified.
Yeah.
And in this case, it is simply a rotation about the x-axis. So you have to repeat so of course, in theory, you would have to do infinitive measurements for all values of alpha, which you see rotates about this axis. And then for every of these initial states, you measure the error, and then you take the largest value. And of course, in this simple example, it follows a sinusoidal oscillation. And then you immediately see that for pi half, you get the maximum value. So I show you again the results, which is, there was some, I explained it a little bit too long. So you see.
And you are mentioning here a square is not equal to 1 identity. Why it is? Oh, because why it is so? Because a square is still a spin operator, right?
Yeah.
So a square will be identity here. Idempotency will be there, right? It's a Pauli observable, right?
No, it's not a Pauli observable. It does not, because it's a sum of two Pauli.
Okay, it's a projector. Okay.
Yeah, it's simply because, it does not behave like a single Pauli observable. You would have to divide it by square root 2. Then it's again a Pauli observable, and then it would be 1. But simply the sum of sigma x and sigma y, it is still a projective measurement, but it's not a Pauli measurement. That's why it is stated.
You just add the 1 by root 2, then that will be enough. Okay.
Exactly. Yeah. But but what happens to this 3-state method is that now you have to measure it. It's because it's not 1. Yeah.
Yeah. But still you have 3-state measurement, right?
Yeah. You have 3 states because you have here psi alpha times A, psi alpha times A. But what you need to take into account is that these 2 additional terms are not only 1 per definition, but they need to be measured. If you do the calculations, you simply find out that they are proportional to projectors.
Yeah.
I can show you the individual measurements. So here, so where is it? That's the first one. Sorry, 1 second. Here. So if you plug in a square, you find out that this is nothing but 2 times projector x square. So it's 2 times projector. So it's always 2. But you have to measure it because it's not identity.
But in what sense then it is state independency? Because you are taking the supremum over all states, right?
Yeah. So you have all this is always plotted against all or several values of alpha. Of course, here, since it's orthogonal to x, it's always the same. But in general, as we see, for example, here for this term, here you have, I need to go back. Here you have a dependency of the expectation value of m on the initial state or on the variation of the initial state dependent on the angle alpha. And you already see here that this will be the correct value. And then if you sum up all these terms, you get something like this, and you immediately see that for the value pi, that this will be the correct error, which again is, as we wanted, is non-zero because it is not an accurate measurement. Therefore, it should have a non-zero error, and this is shown in this measurement.
And then when you calculate the disturbance, you take the different state, right? Alpha. It's a sign.
Okay, very good question. This measurement, for this measurement, we only measured the error. So this is not a successive measurement, unlike I presented before and after. Here we only focused on the error definition. But of course, this is ongoing work. We include this error definition into an error disturbance scenario, but this is it's a little bit due to the state dependency, or due to this to getting rid of the state dependency. This is very complicated to analyze the effect on the disturbance. So there are many parameters, and we're still not happy, but this is work in progress to include this redefined error definitions into the error disturbance scenario.
Okay, I got it. So there's one more question. Maybe it is not exactly related here, but if you may, whether you try to answer it. Can an arbitrary POVM structure be used to generalize the resource theory of coherence? It is definitely not related to this talk. Because resource theory of coherence is completely different.
I don't think there's a simple answer to this. So what's your thought on it? It's
mine. No, I have no idea, because I heard about the resource theory, but I never worked on it, so I cannot give any answer. But it is not related to this talk.
So I will think about it and contact you once I find. But nevertheless, thank you for the questions. Yeah.
Yes.
Okay.
So I think there are no more questions. So Professor Panigrahi?
Yeah. I just want to say thank you for a wonderful talk. Very, very nice talk.
Yeah.
Thank you for having me. It was a pleasure to contribute to your workshop.
Okay. Thank you, Stephan.
Okay. So
let's see when we can meet again.
Yeah, really looking forward to coming to India in the not too distant future, hopefully.
Yes,
okay.
Hopefully, yeah. Okay. Bye. See you. Take care.
Okay.
Take care.
See you via my. Bye.
Bye. Hello, thanks.
Sir, it's okay. Yeah, you're welcome, sir.
Yeah.
So
really, we have wonderful talk.
Yeah, it's a very good talk, but it is a little bit.
Actually,
for students, it's a little bit difficult because it is not.
Difficult topic. Very illuminating, because this is what was required from an experimental perspective.
Yeah, all the experiments, and
you can really see such huge reactors. And
I have seen it. I was there. I know they are
actually, I think the year I met you in Vienna, that was the year you had visited them, no?
Yeah. Actually, I went Vienna around 6 times, I think. I used to visit them for every year.
So I can imagine you have exactly same language like him, so you can talk to him and he's catching you.
Yeah, because we had a lot of discussions. I used to give lectures there around 6-7 lectures every visit. So
very subtle aspect, very beautiful. Okay?
Yeah, sure. Okay. See you soon.